Hi, in this overhead section we're going to talk about remaining issues relating to relationships and how to study them. So far we've been looking at relationships between two quantitative variables in scatter plots primarily, and in this presentation we'll talk about other kinds of variable relationships and other ways to think about relationships more generally. The diagram here on the left talks about the idea that one factor X causes a change or influences the distribution of another variable Y. And so the solid one-directional arrow is causation arrow. The double-ended arrows with a dashed line just signifies that there is an association or a relationship. And so if X causes changes in Y, then you will see a correlation or an association between X and Y. So one example of causation is smoking X causes lung cancer Y. Another possibility is that a factor like Z influences causally X and causally Y, and it makes X and Y look like they are related. So Z causes a change in X, causes a change in Y, and it makes X and Y look correlated. Another possibility is that X causes a change in Y, and that a third factor, Z, causes a change in Y. X and Z are correlated with each other from the dashed arrow, and X is correlated with Y from the dashed arrows. It's not clear, though, in this diagram which or how much of the change in Y is due to X and how much is due to Z. The middle diagram of common response can be given by an example where academic ability Z can influence the undergraduate GPA X of students, and also influence their graduate record examination score for getting into graduate school. Better students, Z, higher, will produce higher GRE scores, and better students, Z, will produce higher GPAs, and that might be the reason why GPA and GRE score look correlated. That would be an example of the middle diagram common response. The last diagram, an example, is during the 1970s, the national speed limit was lowered down from about 65 miles an hour to 55, and that's X, change in the speed limit, and Y is the change or number of highway deaths, and the speed limit change was associated with fewer highway deaths. So there certainly was a correlation, the dashed arrow, between X and Y. The problem was at exactly the same time there was an oil embargo in the United States, and there was very little gasoline around, and so people drove less. And so less driving is Z, and of course driving less gives less driving deaths, and so part of the reduction in deaths is due to less driving. Part of it is due to lower speed and the physics of crashing. And so both X and Z probably change Y, but we really don't know how much from each because they both happen together. The effects of X and Z on Y are confounded. Another way to think about relationships is through a concept called Simpson's paradox. And the illustration of this is for graduate admissions data from the University of California at Berkeley. When we study the fraction of males and females that applied to the university and got in, you can see that about 44.5% of males got into the university's graduate programs and only about 30% of women. And so there was a sex admissions discrimination lawsuit because of this. The university didn't think they were discriminating, so they asked their stats department to help them understand and get out of this mess. And the statisticians looked at the admissions process and they discovered a very important thing. students don't apply to the university centrally in one place. They apply to individual programs. So you have to look at individual programs to understand the issue. And so this data shows the admission and gender breakdown according to the different departments, A, B, C, D, E, and F. Let's look at them individually. So for Department A, what it means is that there were 512 males that were admitted to Program A. There were 313 that were rejected, and that means the admissions fraction down here in this table was about 62%. For females, the admission percentage, far fewer females applied, but 82% of those that applied got in. And so is there evidence of discrimination against females for Department A? And the answer is, well, no, not really. A higher fraction of females than males got into Department A, so there really isn't any evidence of wrongdoing there. Let's take a look at Department B, and you'll see here 68% of females that applied. There weren't many, looks like only 25 of them, but 68% of females got in and 63% of males got in. No real discrimination against females there. Let's take a look at Department C. It's 37% of males got in and 34% of females got in, and at least finally the direction is in favor of males, so at least this is a little bit suspicious, but boy, it sure isn't a very big difference. 37%, 34%, that doesn't seem like a really big difference. Let's take a look at Department D. Looks like about 35% of females got in. Looks like about 33% of males got in. There's no real advantage for males there. Let's take a look at E. A little bit of advantage for males there, a couple of percentage points, but it's not very big. Let's take a look at F. A little bit of an advantage for females, 7% getting in as opposed to 5%. And so here we are going through all the departments, and there really is nothing very suspicious about what's going on. The male and female admissions fractions are either very similar, or females maybe with a little bit of an advantage in a lot of the departments. So how is it that females are at a disadvantage overall? And the answer is because males apply very heavily to programs A and B. If you look at the application numbers for males, they apply very heavily to departments A and B. And if you look at the admissions fractions for A and B, just about everybody, or over half the applicants, get in to departments A and B. It's very easy to get in to A and B. If you look at where females apply to, they apply very heavily to departments C, D, E, and F. And if you look at those fractions, they are very small, particularly F. Very small fraction getting in for those that apply. And so the problem is that the admissions, sex is related to program, and program is related to the admissions fraction. And so there is this confounding and lurking variable that is complicating the relationship between sex and admission. So we want to study the relationship between sex and admission, but the problem is that sex is related to program, which is the thing that is related to admission. And so it looks like the whole story is getting driven by Z, but it looks like there's a relationship between X and Y, but it's really driven by Z, the program. And so this is an example of Simpson's paradox, where the relationship between two variables is being distorted by a third variable called a lurking variable, the variable z. So a lurking variable can falsely suggest a relationship, or it can hide one. If you think about some examples, you will notice that there is a very strong relationship between the number of firefighters that are at a fire and the amount of damage that's done. And so you really wouldn't conclude that the firefighters are damaging the building. The damage is being driven by the severity of the fire, and so is the number of firefighters. That's a common response diagram that we saw previously in a photo like diagram like this one. There's a relationship between firefighters and damage, but that relationship is being driven by a third factor, z, the severity of the fire. Another example that's given here on overhead 18 is a negative relationship between wine drinking and death rates from heart disease. Turns out that nations that do consume much more wine per capita tend to have very much lower death rates than countries that don't drink so much wine. The problem here is that wine drinking is also associated with other dietary and health effects like the Mediterranean diet. Italy, Greece, France, Spain all typically have much lower heart disease rates than countries like Denmark and the UK and Sweden and some of the northern European countries. The United States, for example. And part of that might be the wine drinking, but part of it might be dietary factors like the Mediterranean diet with more fish and olive oil. And so the response, death rates, Y, is confounded with the wine drinking X and other dietary factors, the lurking variable Z. One of my favorite examples is the relationship between alcohol consumption, X, and lung cancer, Y. Any study that's ever been done finds a very strong connection between alcohol consumption and lung cancer. And so, does that mean that alcohol consumption causes lung cancer? And the answer is no, of course not. The lurking variable that's complicating that relationship is the lurking variable of, you guessed it, smoking. And smoking is related to alcohol consumption, and it's the smoking that's related to lung cancer. And so that's why it appears that alcohol consumption is related to lung cancer through the other effect of smoking. Other interesting relationships are things like the number of golf courses. As that has gone up, the divorce rate has gone up. And there's other really interesting examples for this. So establishing causation is a really important kind of relationship connection, but it really takes a lot of work to establish causation. You have to have strong association. You have to have the association be consistent across lots of studies. You have to have a dose-response relationship that more of the risk factor is associated with more of the response. The exposure or the cause has got to come before the health outcome or whatever it is. And you have to have some kind of story or plausible mechanism for how the cause works. So now that you've seen some of the difficulties dealing with studies, be very careful when you design your own studies. Control for lurking variables and confounding factors. Be very thinking about this and alert when you read other people's work. Think about variables that they didn't measure but should have. Think about important variables not controlled. And as the last bullet points out, I think this is probably maybe the most important thinking skill that you will learn in this course. When you think about how variables are related, think about how they might have arrived to be related. Are they related because of some causal mechanism, or are they related just because there are other third factors driving the story for both of them? So Here's an overview about studying relationships. We've studied a lot of the first bullet, quantitative against quantitative variables with a scatter plot. If you want to study a quantitative variable across the levels of a category or a qualitative variable, that's done with box plots, side-by-side box plots. We'll see some examples of that. And when you want to compare two category variables together, you either do that with bar plots or pie charts. So here's an example of the quantitative variable across the levels of a grouping variable with box plots. Here's some data from the Sleuth 3R package library, and it is studying the Armed Forces qualifying test, kind of skills test, in 4 groupings, quartiles, the lowest quarter, the second quarter, the third quarter, and the upper quarter of scores. And then so that'll be the grouping variable, which quarter of test score. And the quantitative variable is the income later in life. So these tests were done in 1979, and we're going to study their incomes in 2005 and 2006. And so you can see we have our subjects, we know which skill IQ quartile they're in, and we know their income. And here is the side-by-side box plots. We have our qualitative category variable about the skills test quartile, groupings 1, 2, 3, and 4. And then we have our quantitative variable about annual income. And you can see from the box plots there's a lot of outliers. There's a lot of really unusual high earners. But as the general trend in the boxes tends to go up. If you're in the lowest skill level, you have the lowest income, and it's pretty uniformly low. You just don't have a lot of earning ability. As you move up the skill level, there's more diversity in the box and the typical income going up. And so that talks about the fact that there is a pretty clear relationship between IQ and earnings. If you want to study a category by category variable, we will tend to do that with either a series of bar charts or pie graphs. And what you're looking for is whether the pattern in the bars or the pies for one variable stays the same across the levels of the second variable. And so here's an example. We want to know whether the previous letter grade that a student got is related to the letter grade in a future or later class. Is there a connection between how a student did before in a class, maybe a different class, but some other class, and how they're doing currently? Is there a connection between the grades? So one way to do that is to look at a bar plot for the current course's academic grade, and that would be the A minus, B plus, B minus, C. That's across the bottom axis of all these panels. And these bars are broken into the grade they got in a past class. So the way to read this is in the in the upper left corner. These are all people who had an A in the last class. How are they doing currently in the current semester class? And you can see that they typically are doing very well. Almost everybody is an A or an A minus in Bs. There's a few people struggling in this particular current class, but it's kind of unusual. Most people are doing well. On the other end of the scale, this F panel is everybody who got an F in a previous class. How are they doing in this current one? Well, they're typically doing bad. They're getting Fs or Ds or Cs, and they're just not doing very well. Very few are doing extremely well. And so there is a relationship between these variables. No relationship would mean that it doesn't matter what panel you look at, the distribution that you see in the bars would be the same across all the panels. And you can see that's not true here. In this panel, we typically have good grades. In this panel, we typically have bad grades. In fact, in all of these bottom panels, we typically have bad grades. And That's not true in the top panel. So there is a relationship between these two category variables. Other kinds of more complicated relationships are possible, where you might want to use many variables to understand a relationship with a single response variable. And there are other courses that you would take to study this. At UMM and at other universities, advanced courses tend to teach you how to study relationships with many variables at once. Just to give you a flavor of how this might work, let's think about how the AFQT Armed Forces test relates to future income. You've seen an example of that before, but let's also add in another factor like the amount of education. So here we have two predictive factors, IQ and education, that are going to be used to try to discuss income. And one example approach is called a regression tree, and this is kind of a big data mining kind of approach. And what it does is it shows you the factors that help distinguish between the income levels. And the way to read a chart like this is at the very top we have about 2,600 subjects, and here is their average income. And what we do is we try to find the factors that most distinguish between big and small incomes. And the single factor that we find that is the most discriminating between who are high and low earners is education in years above 15 and a half years. If you think about that, high school is about 12 years, another 4 years is 16. And so basically what this says is if you have a college undergraduate degree or higher, that is the best split to distinguish between who's got high and low income. The higher earners are the high education people over here. If you look at this average income, it's quite a bit higher than the average income for people that have less than a college degree. For each of these piles of subjects, is there another factor that might split them apart into different income levels? Well, if you have low education, or at least relatively low education, the next factor or variable to split is on the IQ variable. If you're lower than 45.7, you have lower incomes, and if you have a higher intelligence level, you tend to earn more. And these splittings continue until we sort of fully understand the variables that determine income. For the high education people, you'll notice it is the intelligence again that is split, although it's split at a much higher intelligent level. Those above about 70.6 tend to have much higher incomes, even among the high educated. Lower IQ tends to have lower income. Higher IQ tends to have higher income among the more educated. So this would be an example of a split regression tree pattern that would help you understand the relationships between more than a couple of variables. And the final overhead here, 32, goes through the discussion we just had. Let me know if you have questions about relationships or if you need to take another course in statistics to learn more about this.